Hello everyone, welcome back to your favorite place, Calculus Fun Room. Good morning, good afternoon, good evening, whatever time it is here. So in this section, now that we have developed the ideas of limits, and we spoke in our last video very specifically about limits in a generic manner mathematically, what we can do then is come back to the basic idea of continuity that is very intuitive, we've seen for a long time since algebra, if not sooner than that, before that. And let's give a rigorous mathematical definition to this idea. So usually like in an algebra class or some class back in that manner, we talk about continuity being we can sketch the graph of a function without ever picking up our pencil. And that's how we kind of intuitively, visually describe that idea of continuity. Now what I want to do is take a look at this graph and let's look at some particular points where we might not have continuity. So let me resketch a graph down here. I'll move it over here actually. So let's say at x equals 3, our graph is continuous, and then let's say at x equals 5 we have what we call a removable discontinuity, and then let's say at x equals 8 we have what we call a jump discontinuity, and then let's do it like a vertical asymptote here at x equals 10, let's say. So here's some function f of x. Let's just speak in general terms here. So what does continuity mean? So if we look at x equals 3, as I travel through the value where x equals 3, I have continuity. I never had to pick up my pencil there. So we see continuity at x equals 3. Now let's take a look at x equals 5. At x equals 5 we don't have continuity because as I come in from the left I have to jump up to that point and then jump back down to continue sketching the graph. And again we call that a removable discontinuity. Now if we take a look at terms of limits, what is going on? What is wrong there? So if we suppose that, let's say the y value here, so as x approaches 5, let's say that y value is, let's say 1, and let's say the function value there is 2. So what we notice in this case as we approach 5 from both sides, the function has a value in its limit of 1, right? And then our function value at 5 is something different. So what we could note here is that the limit as x approaches 5 does not equal f at 5. So we need that to happen, right? We need the limit and the function value to be the same, and that means we're not picking up our pencil. In fact, let's come back to x equals 3 here. The limit from both sides was 2, and the function value is 2. So if we looked at the limit as x approaches 3, that limit was 2, and the function value at 3 is 2. So we can see in that case, for this particular graph, as we approach 3, the limit and the function value are equal to each other. Now if we come out here at x equals 8, notice that x equals 8, if we take a limit as x approaches 8, right, what value are we going to get there as our limit? Well, correct. As we approach from the left, looks like the y value is trying to get to 2. As we approach from the right, the y value is trying to get to 1. So in this case, as we approach 8, the two-sided limit, right, does not exist. Now we do have a function value there. The way that I sketched this graph, f at 8 was equal to 1. Right? But notice, again, I'll say it in this manner because this is how we define continuity. So these two things are not equal to each other. Now, if we take a look at those three situations and we look at, what failed, right? So if we look at this first limit here, this first exploration at x equals 5. What failed there? Well, the limit existed at 5, right? It was 1. The function value existed at 5, it was 2, but those weren't equal to each other. If we look at the second scenario, we had equality there, right? So the limit did exist, it was 2, the function value did exist, and they were equal to each other. And that was where we got our continuity right there at x equals 3. And then if we look at that last statement that we wrote, what failed there? Well, in this case, the limit didn't exist. So if the limit doesn't exist, then there's no way those two quantities can be equal to each other. So we have a formal definition of continuity that we state in this particular section. So again, now that we have looked at limits in a very rigorous, more generic manner, then we can come back and we can define a really simple concept of continuity, never picking up my pencil. We can define it in a much more rigorous manner. So we would say something like this. We would say a function f of x is continuous at x equals a if the limit of f of x as we approach a is equal to f at a. So again, there is the definition of continuity, and there's really three things that are happening there, right? The limit has to exist, the function value has to exist, and they have to equal each other. So three basic things that have to happen here, right? The limit has to exist, the function value must exist, and you know what? Limit must exist, I'm going to say as x approaches a, right? F must exist, F must be defined at x equals a, and those must be equal to each other, right? A has to equal B from what we have up there, right? So there's really three conditions we really have to take a look at here. And in fact, I'm going to scroll back up to my graph real quick, because if we look at, let's say, the function being defined, in all three of these cases, f at 5 was defined to be 2, right? F at 3 was defined, and f at 8 was defined. So we actually never had that fail in that example, and that's because I completely forgot to come out here and look at x equals 10, right? So if I have a vertical asymptote at the function, or if there was just a hole where we don't have a definition, then the function value isn't even defined. So when we look at x equals 10, we fail everything. The limit doesn't exist from the left or the right, and the function value isn't even defined in that case. So again, really simple concept. What is continuity? I can sketch a curve without picking up my pencil. How do we define that in a more rigorous manner mathematically? We need the tool of the limit to be able to make or state that definition. All right, let's take an example here and take this conversation a little deeper. So let's look at a couple different functions here. Let's determine where each function is discontinuous. Determine where each function is discontinuous. So let's look at, let's say, f of x equals x squared minus x minus 2 all over x minus 2. Now, from an algebraic conversation, right, we can notice there's division by 0 right at x equals 2. So we know just from the algebra of rational functions, at x equals 2, the function isn't defined. So we're going to note, right, that f of 2 is undefined. Now, just for the sake of completeness, what would the limit of f as x approach 2 end up being? So in this case, the numerator factors x minus 2 times x plus 1. So just like we saw in the prior section, in this case, that discontinuity removes itself, and what we're getting is 3. So when we're looking at the definition of continuity, right, our limit does exist, but our function value does not exist, right? So, we're basically saying, does the limit equal the function value? I'm going to say question mark, right, as x approaches 2. And in fact, let me type or write f at 2 there. Is that true? And the answer is no, since f at 2 is undefined. All right, let's take a look at another example. So let's say letter B. We have, in fact, let me stop for a sec. I'm getting ahead of myself. Let's say for letter B, we look at a piecewise defined function. So let's say we have 1 over x squared, and that's the function definition as long as x is not 0. And then let's say f of x is defined to be 3 at 0. Now, if I just stop for a second, when we think of like the graph of 1 over x squared, looks something like this. Right? And then at x equals 0, we're defining the function to be 3. Now, obviously, visually, we're picking up our pencil, right? So there is no continuity at this point, but let's discuss in terms of our limit definition. So if we take a look at the limit, right, the limit of 1 over x squared as x approaches 0, right, that's infinity. And we can see visually, right, that the limit as we approach 0 from the left is equal to infinity, and the limit as x approaches 0 from the right is also equal to infinity there. Now, then when we look at the function value, right, f at 0 is equal to 3, so that is defined as well. So then, our question is the limit of f equal to f. I'm going to put a question mark. Is that true? And the answer is no. Right? So, infinity does not equal 3. So this function is discontinuous at x equals 0. Now, I didn't make that formal statement up here. I really should come back up to this prior example here and say, the question was, where is each function discontinuous? So I'm just going to say, f of x is discontinuous at x equals 2. And then this one, we're discontinuous at x equals 0. Let's take a look at example 3. So let's look at the function. Let's say f of x equals the absolute value of x. And we're finding the point of discontinuity. Now, if we think about the graph of absolute value, right, it's that V-shaped graph. And we're looking where this function is discontinuous. We would never have to pick up our pencil here in this case. Right? So we know that this function is continuous everywhere. And how would we, prove that in essence? So let's think about the definition of absolute value of x, right? So if x is a positive number, or 0, then whatever the x is, that's the absolute value, right? So if x is 3, absolute value of 3 is just 3. Now, if the x value is negative, what we're doing is taking the opposite of the x value. Right? So if x is negative 3, the absolute value of negative 3 is the opposite of negative 3, which is positive 3. So here's our piecewise definition. Now, if we're looking for, where am I discontinuous? I know visually that I'm not discontinuous at all. So what I need to do technically in this scenario is show that it's continuous at every value in its domain. So I don't want to look at a specific numerical value. I want to look for all possible values, right? So for any value x equals a, right, where a is an element of the reals, so what would the limit of x, absolute value of x, be as x approaches a? What is that limit? So, if x was 3, I'm just going to use the direct substitution rule, and if I plug 3 in, I get 3. So no matter what value of a I get, I plug it in, I get absolute value of a, which is a. So For any value of x within the reals, the limit of my function is equal to absolute value of a. In fact, let me say absolute value of a, and that's equal to a, right? And then we have to consider, what is f at a. So again, any x value that I plug in, I'm going to take the absolute value of that number, and I'm going to get a. So these are true, right? I'm asking, does the limit of f of x equal f at a? The limit of f as x approaches a equal f at a. And yes, that is true, right? Our limit was equal to a, and f at a was equal to a. So f of x equals absolute value of x is continuous for all reals. Continuous on the set of all reals. So there are no points of discontinuity for the absolute value function. So let's come back here and have a more generic conversation about intervals of concavity, right? So for my absolute value function, it's continuous everywhere, right? So it's an interval of continuity of, in this case, all reals. Now, if we think in particular about what is continuity, kind of from prior knowledge, right? So think about polynomials. Or actually, before I jump on polynomials, let's think about the root function. Let's take a look at the root function. Right, let's consider f of x to be equal to root x. So maybe the question would be here is like, where is f continuous? Where is f continuous? Now again, visually, we know here's the absolute value function, and we know it's continuous for any value of x greater than or equal to 0. We know that that's true. That's where it's continuous, right? Or in an interval, we could say 0 to infinity. So based on our prior knowledge, right, what I don't really want to have to do here is prove for every value of a this function is continuous. Now we could, and if you, maybe say you're going to major in math, you can take a course called abstract algebra where you would actually do a proof showing that function root x, right, is continuous for 0 to infinity, just like we did for the absolute value function. But what we want to do is we want to say, the purpose of this course is not really to do rigorous mathematical proofs. What we really want to do is focus on some concepts that are very important and then apply those concepts, right, to some meaningful situations, some applications. So in this particular situation, let's think about what are the functions that we're familiar with, right? What functions have we seen in our past, and where are they continuous? Now in a lot of textbooks, they'll give you like a theorem is what they'll say, something like this, right? And they'll say that any function f of x is continuous on the interval I, as long as, right, if f is defined at all values of x contained in that interval. So basically we're saying the function is continuous on its domain, right? In layman's terms, f is continuous on its domain. So just like with our absolute value function, or let me scroll back up for a sec, right? Our absolute value function, as long as why am I saying absolute values? Look at the root function. As long as the root function is defined, then that function's continuous inside its entire domain. So typically when we're asking a question in this course of where is a function continuous, we're really kind of falling back to an algebra course, and we're just looking for the domain. What is the domain of the function? However, we can have the conversation in a little bit more rigorous of a manner as necessary to define that continuity. We now have a definition of what it means to be continuous at a point x equals a. So we can talk about for any value of x in some interval, right, as long as the function's defined, it's going to satisfy that definition, that the limit of f is equal to the function value for any value in that interval. So to summarize the conversation that we would typically have in this section, and then we'll take a look at a couple examples. So there's a theorem that basically says what we already know, and that the following types of functions are continuous at every number in their domain. That's kind of the key here. And as long as we are within the domain of this function, then the function is continuous. So polynomials, and think about this, polynomials are continuous everywhere, all reals. Polynomials never have division by zero. Polynomials never have square roots of negatives, right? So those are continuous everywhere. Right? Rational functions will be continuous at any point in their domain. Right? Same thing with root functions, just like we saw with the root x function a minute ago. And as long as we're at an x value in its domain, it is continuous at that value. Trigonometric functions, sine, cosine, tangent, right? If we think about tangent, it has vertical asymptotes at every multiple of pi over 2. But as long as a value of x is in the domain of tangent, it's continuous in that interval. Any inverse trig function, exponential functions, and logarithmic functions. So usually, so we've got two more things I want to do here. Right? Let's take a look at a couple examples where we just kind of apply this theorem. We find some intervals of continuity. And then let's discuss the intermediate value theorem. So let's suppose in this example, we're going to determine where, let's say, f of x equals ln of x plus, let's do inverse tangent of x over x minus 1. Let's determine where this function is continuous. So what I'm going to do is I'm going to break this into pieces, okay? Let's take a look at ln of x for just a moment. If we think about, the graph of ln of x, what we know from an algebra class, ln of x looks something like this, right? We know that the domain of the logarithm is x strictly greater than 0. If we look at the inverse tangent function, inverse tangent is graphically the inverse of the tangent, right? So it looks roughly something like that. So its domain is all reals. So we have a domain of all reals for inverse tangent. And then if we look at x minus 1, so technically x minus 1 has a domain of all reals as well. However, the way that x minus 1 is placed in this function, it is in the denominator. So within the context of my function f, x minus 1 can't be equal to 0. So we know x can't be equal to 1, for our function f of x. So if we look at all three of these, right, let's take a look at the first function, ln. We know my domain has to be everything greater than 0. For inverse tangent, we know we have all reals as its domain. And then for x minus 1, we know x can't equal 1. So let's say, here's 0. Let's say here's 1. Right? So within the domain of my function. So I can have any other value of x in the denominator except 1. Now when we're looking at, where is this function continuous, right? Remember, we're really looking for where's the domain of the function in essence, right? And so when I'm looking at each of these sets, the domain of each set of the function, I'm looking for the intersection, right? Where can I define all of these things? So if I look sort of here, right, I can't have anything to the left of 0. That's not valid. I can have anything to the right of 0 except x equals 1. So we're going to say f is continuous. Continuous for, so we can't include 0 and we can't include 1, but any value between 0 and 1, my function is defined. And then anything greater than 1, so from 1 to infinity. And now when we were doing this problem and any other problem similar to this, we're really utilizing this theorem to help us, right? We know that the logarithm, the inverse tangent, right, all of these specific pieces of functions that make up my f of x in this problem, right, we know that on their domain they're continuous. So we're able to make this leap, right, that, log of x, right, is continuous as long as x is greater than 0. So we're basically building on our prior knowledge from an algebra or maybe a trig class. We're looking at those functions being continuous on their specific domain, and then in this example, applying that concept to a particular function ln x plus inverse tan x over x minus 1. So now that we've discussed this continuity, one other thing that we can build to is another property of limits. So if f is continuous, I'm going to state this in a generic manner, right? Very general. If f is continuous at some number b in its domain, and g as x approaches a equals b, right, then the limit of f composed with g as x approaches a equals f at b. And what we really want to do here is state this in terms of a property of limit. So what we in essence just wrote was that when we have a composition of two functions, we can move the limit process inside the function f. Now, this should not be surprising. So let's call this another property of limits that we would go back and add to our prior section. And remember, in that prior section, we had discussed, like, if we have f of x raised to the n, how we could move the limit process inside the exponent, then raise it to the power. So this is what I just boxed in up here is a more general form of that concept. Right? If we think about what we wrote down here from our prior section, this is a composition. The f of x is the inside of the power of n function. So what we just wrote in this box is a much more general manner of something we already saw in the prior section. Also remember we had, what was it? We called it the nth root of f. We said the limit of the nth root of f was the nth root of the limit of f. That was another property that we wrote in that prior section. And again, that's an example of that more generalized form that we just put into that box. So again, let's tack this back into our properties of limits. So let's take a look at an example where we would apply that property. So let's suppose we want to evaluate, let's say, the limit as x approaches 1 of, let's do inverse sine of 1 minus x over 1 minus x squared. Now, using that property we just wrote, this is a composition. The arc sine, right, inverse sine is the outer function, and then that rational is the inner function. So we can move the limit process inside the composition. Now I'm going to go ahead and skip a step of work, and I'm going to factor the denominator. Right, and again, just like we saw earlier in that prior video, and if I plug x equals 1 into this rational, I get 0 over 0. So again, usually in the safe confines of this course, for now, until we get to some later sections, this usually means there's some algebra cleanup. So I went ahead and did the factoring. I can see I'm going to get some algebra cleanup. So I'm really looking at the inverse sine of, and then I have the limit of 1 over 1 plus x as x approaches 1. So I can go ahead and evaluate that limit inside. I'm going to get 1/2. So now that we have completed the limit process, now I'm asking what is the arc sine of 1/2, and that would be, what would that be? Pi over 6. Now you can look at a unit circle there if you want. When I took trig, I was never allowed to look at a unit circle, so I always had to memorize my reference triangles. So 45, 45, 90 has those sides, 1, 1, root 2. And then 30, 60, 90, so smallest angle is 30. It gets the smallest side opposite it. So I'm asking here really, right, what is the inverse sine of 1/2? I'm saying what angle do I take the sine of to get 1/2? And I would take the sine of 30 degrees because sine is opposite over hypotenuse. So 30 degrees would be pi over 6. The last concept we're going to look at in this section is going to be called the intermediate value theorem. So what I want to do here first is when we write this theorem, it can sound kind of confusing, and I want to sketch a graph to visualize what the theorem is saying, and then let's write the verbiage of the theorem down for ourselves. So this is, in a visual manner, I'm going to basically consider a continuous function on a closed interval from a to b, whatever that function looks like. Lots of different types of functions that can exist on a closed interval. So basically the intermediate value theorem says if we have a function that is continuous on that closed interval, then when I look at the y values, the function is going to take on every possible y value between the two endpoints. Now that seems kind of weird and silly. There's a really powerful couple powerful uses of this theorem. So again, visually, the idea is that for a continuous function, the function will take on every intermediate value between those two endpoints. Now we could have a situation, where a function takes on values multiple times, right? So between f at a and f at b, we could take on y values multiple times, right? So if I drew a horizontal line here, right, whatever this y value is here, the function's hitting it 3 times. So the way that the intermediate value theorem is going to state this, it's going to basically say there's some number, let's call it c, that lives between a and b, such that the function has a y value at x equals c. All right, so let's write out this in words, and then we'll talk about how we can use this. So the intermediate value theorem says something like, suppose that f is a continuous function on the closed interval from a to b, and what we'll do is we'll let n be some number. So let's say over here on my graph n was this number. So we're just going to let n be any number between f at a and f at b. And mathematically how we typically write that is f at a is less than n is less than f at b, right? That's usually how we say in between. And we're going to consider that endpoints aren't, we're going to consider that the function's not equal to itself at the endpoints. Right? So we're going to consider this is not a horizontal line. We have some increasing or decreasing throughout that interval. So then our conclusion is, right, as long as f is continuous, then there exists a number, I'm going to say x equals c, and that's in the open interval. Right? So we don't want c to be at the endpoint, right? We want c to be between a and b. It's not going to be at an endpoint. And f at c will equal that n number. Now we're writing this in a very arbitrary manner. And again, I'm going to resketch, I'm going to erase all of this over here, resketch this to just have that conversation one more time in a visual manner. Come on, go away. Okay, so we are considering a function that is continuous on a closed interval. And when we look at the endpoints on that closed interval, when I connect these two with a continuous function, there has to be some number c and in fact all numbers between a and b, will take on at least once some value, intermediate value between f at a and f at b. So something along those lines. Now again, as I mentioned a minute ago, we're going to utilize this theorem in a couple different ways. In this section, there's one way we're going to use it, and then we'll see in a couple sections from now, we're going to look at what we call the mean value theorem, and we will utilize the intermediate value theorem in the proof of the mean value theorem when we get to derivatives. So to take a look at an example here of how we would apply this, and before I do this example, what I want to do is just note how we will use it for the moment. So what we're going to do is like find a zero of a function. So in a visual manner, if I have a polynomial function, some polynomial function is smooth and continuous, and what we're looking for is this zero. What is that zero there? So what we're going to do with the intermediate value theorem is we're going to show that f at a is a negative number. We're going to show that f at b is a positive number. And since f is continuous, we know that it has to take on all the y values between f at a and f at b. And there's going to be at least one time it takes on the y value of 0, and that will be at x equals the root, x equals c. So that's how we're going to utilize that in this example. And again, this all hinges on the fact that the function is continuous, right? If the function isn't continuous, it could jump over the x-axis, or it could completely avoid the x-axis, right? So this theorem is only useful for continuous functions, which honestly, that seems quite restrictive, but we will see again how useful this really is here. So let's take a look at an example, and let's say in this example we want to show that there is a solution to the equation 4x cubed minus 6x squared plus 3x minus 2 equal to 0 between x equals 1 and x equals 2. All right, now we could take out a calculator and graph this and show that that's true, and I want to do that at the end, but let's just show the analytical pencil paper work that we would utilize here. So what I'm considering then in this case, I'm going to leave this graph up here. This is my function f of x, right? So I'm going to consider this as my function f of x. So what I want is for f to be negative or positive at some point. So I want to know at x equals 1 and at x equals 2, what are the y values on this function? So we could pretty quickly figure that out. So let's say note f at 1. So if I plug 1 in, I get 4 times 1 cubed minus 6 times 1 squared plus 3 times 1 minus 2, and that is going to equal negative 1. And I'm going to point out, that's a negative number, right? So we know f at 1 is right here. Here's f at 1. Let me just say that's 1. All right. Now, let's note then what is f at 2. So if I plug 2 into that function, I'm going to get 12. And that is positive. So f at 2 is somewhere up here, let's say, at 12. All right, now as long as f is continuous, then I know some point here, whatever that graph looks like, I'm going to have a 0 at that number, x equals c. Now, the question then is f continuous? So let's also note f is a polynomial. And just like we discussed a few minutes ago, it's going to be continuous everywhere, right? In particular, it's continuous on our interval from 1 to 2. Right? So we're going to say, so by the intermediate value theorem, there exists a value x equals c in the open interval such that f at c equals 0. And let me just go ahead and tack on, right? I'm going to say, f at 1 was less than 0 is less than f at 2. I just want to point out in that case, the reason I made that statement, right, is f at 1 is negative, f at 2 is positive. Just wanted to formally point out that 0 is one of those intermediate values that the function could take on. Now, in particular, all we have really proven is there's at least one 0. There could be 2, there could be 3, there could be 4, but this problem asked us to just show that there is a solution. It didn't say show that there's 3 solutions, and it didn't say find the solution, right? It just said show that there is a solution. So let's take out a graphing calculator and visualize this idea. So I brought up my graphing calculator, I typed in the function that we're dealing with, and then I want to go ahead and graph. And we can see obviously between 1 and 2, the function has a root. Now it has 1, and that was all we were really asked. Show that there is a root in the interval 1 to 2. Now the reason that I did this, first of all, was so we could visually check. Second of all, to point out to you that when we're using our calculator to find a 0, we have to basically use the intermediate value theorem. Well, there's more to it than that, and actually a little bit later we're going to discuss what we call Newton's method. Newton's method is actually the program that runs on the calculator to find a 0, but in order to run Newton's method we have to give it the conditions of the intermediate value theorem. And let me point out to you what I mean. So if I want to calculate a 0, I'm going to hit second, trace, and I'm going to punch number 2 to find a 0. Now, it always asks me for a left bound. So it's like finding a, right? So between a and b, I need an a value that's negative. So I'm going to move a little bit closer. So I'm picking, let's pick x equals 1. Let's call that our left bound. I'm going to hit enter. Now it wants a right bound. So I could trace until I'm to the right of the 0. Just for fun, let's go ahead and punch 2. And hit enter, and there's my right bound. It's up here somewhere. So I have told the calculator somewhere between 1 and 2 is my 0. So the calculator knows now that we have satisfied the conditions of the intermediate value theorem, and it is going to run a program called Newton's method. It's a slight variation of Newton's method, but it's going to run this program and it's going to find that 0. Now what's kind of cool here, so it wants me to give a guess, right? So I'm supposed to move my blinking cursor somewhere back close to where I think the 0 is. Say, yeah, I think the guess is roughly here, and then it finds that 0 for me with actual that's really accurate. There's some excellent accuracy to that approximation. When we get into chapter 3 and we talk about derivatives and rates of change, we'll actually learn about Newton's method. It's really cool. Any of you going on to be computer scientists, it's a really simple type of program to calculate. All right, that is everything I wanted to take a look at in this video for this section. In the next section, we're going to take a look at another conversation of limits, where we look at limits at infinity, and we'll apply that graphically to vertical asymptotes and a couple other concepts. Look forward to seeing you in the next video.